Happy lesson 14, everybody. We're going to talk about roots of quadratic functions today. This is just an extension of all this quadratic stuff we've been talking about. We're actually going to do something with all the skills that we've been reviewing and learning. Your essential question is just, what are the roots of a quadratic function and how are they found and how do they relate to the real world? Start off with this definition right here. Right, so here's what a root is. It's the point where the dependent variable goes to 0. That's just math mumbo jumbo for saying that the y coordinate is 0. So if you plot a point, you go over x and up y. Well, if you don't go up any y's because you're at 0, then that means you're sitting on the x-axis. So roots can have a bunch of different names. See right here? They're also known as x-intercepts, zeros, and solutions. If you hear or read a problem and it asks you for a root, an x-intercept, a 0, or a solution, that simply means you're finding the same thing. Just figure out where the graph has a y-coordinate of 0 or lots of y-coordinates of 0. So right here on this little piece, we're just going to draw some quick parabolas and talk about the different kinds of roots you could get. We talked about them a little bit when we were completing the square. When we started getting two answers, that's where we talked about this. So if you have a parabola, could go like this, it could be fat or skinny, it could be upside down, but it touches the x-axis 2 times. That means it has 2 x-intercepts, one right there and one right there. Those are the roots right there. Those are the zeros. Those are the solutions if you were solving the quadratic equation that goes with this purple parabola. If you solved it using completing the square, that would be the 2 answers you got right there. This is like a picture representation of your answer. So we say that this parabola has 2 real roots, or 2 real solutions. Real because they're real numbers. A positive number, a negative number, they might be decimals, they might be whole numbers, but they're real. Secondly, we might have a parabola where only the vertex touches the x-axis, like this. If only the vertex is touching, then we have only one solution, so one real root. The last option is, what if your parabola doesn't touch the x-axis at all? If that's the case, then we say it doesn't have any real solutions, but instead it has 2 imaginary roots. Because at this point you would have to imagine them for them to exist, because that parabola is not going through the x-axis. Alright, so let's look at an example here. Determining the roots of each function. So let's look at this first example. Here I've got a picture representation. Remember that pictures and tables and equations are all exactly the same thing, they just are different models of the same thing. So the first thing I want to do is draw right here and show that I see where that parabola is crossing the x-axis, because that's where I'm going to find the roots. It's where it crosses the x-axis. So there's one answer right there and a second answer right there. So the roots are the coordinates of -1, 0, and 2, 0. That's it. That's the roots. That's the zeros, or the solutions, or the x-intercepts. Remember, it all means the same thing. Over here in example 2, I have the same situation, but this time it's a table representation instead of a picture. You could put these in your calculator and graph it and see a picture. You could draw yourself a little sketch. Oh, just kidding. Sorry, we don't really want to do that. Anyway, over here you could draw yourself a quick little sketch and you could plot the points to see what the parabola was going to look like. Or you can remember the definition of roots. It's where the dependent variable goes to 0. Remember, y is the dependent variable. So you're simply looking for where the y is 0. Well, if I scan down this table right here, I look right here and see, oh, that's a -4. Now, that's not what I'm looking for. But look right there. Here's where the y is 0. And here's another place where the y is 0. For a quadratic, it's never going to have more than 2, so I know that I found my 2 answers. Those are the 2 roots. Be aware that problems and problem creators really love to throw this situation in at you right there. If you think about it for just a minute, you'll see why it's tempting. When students start looking for roots, they just look for zeros and they write down every one that they see. In this particular case, though, that is not a root because if I were to graph this over 0 up 6, that's where the parabola runs through the y-axis, and that's not helpful to us when we're finding roots and solutions. So this is not a solution. Even though you see a 0, it's in the wrong spot. So be paying attention to that. Here I'm back to an equation format or an expression format, and if it wants me to solve it and find the roots, we already know how to do that because we've been completing the square for days and days and days now, right? First thing I'm going to do is set it equal to 0 because that's what our quadratics always have to equal when we're trying to solve them. Doesn't matter what method you're using. First thing is move that 15. So I'm left with the quadratic and a whole. Remember to fill in the whole by dividing the middle number by 2. That gives me a 4. And then you square it. That gives me a 16. Keep your equation balanced and then factor it down. Solving for x, so that means get x all by itself. If I square root both sides, then I'm left with plus and minus 1 because the square root of 1 is 1. 1 times 1 is 1, right? Check your calculator if you're not sure where that came from. Last step to get that x by itself is right there. So I'm going to write the answers over here to the side. X equals a positive 1 and a negative 4, so that's a negative 3, or a negative 1 and a negative 4, which is the negative 5. So there's my two roots, my two solutions right there. Over here on the right side, we're just going to make a quick sketch of what this parabola might look like. Now, we don't have enough information to make an accurate drawing, but we can do a quick sketch. I know that these two numbers right here represent the x-axis, so I can go negative 3 and plot a point, and then I can go out to the negative 5 and plot another point. I know that the parabola is going to run through those 2 points. Another thing I know is when I look at this original equation, look right here. Boop. It's positive. If you remember from our discussions at the very beginning of the year, when the quadratic is positive, it opens up. When it's negative, it opens down. Well, I know for sure this one is going to open up. So I'm going to draw a parabola, something like this. We don't know how skinny, we don't know how wide, we don't know how far down the vertex is, but it doesn't matter yet. We'll get to that in the future. So there's your solutions. How about this one? This time it's a full-on equation. Y equals this quadratic. So I'm going to solve it. I'm going to change that y to a 0. And then I'm going to move the 6 out of the way and just finish completing the square. I'm going to rewrite this so that the 0 is on the other end. That way it makes more sense, because that's how we've been looking at them. Is everybody okay with that, I hope? I don't know why I asked you a question you can't answer me. So check it out. Move the 6 to the other side. Divide this one by 2. 2 divided by 2 is 1. Square it, and you still get 1. And don't forget to add it to the other side. When I factor it down, it looks like this. So now I'm going to square root both sides. That leaves me with, oops, square root up here. Square root both sides, and I'm left with x plus 1 and both versions of the square root of 7. Move the 1 over, and I get x equals negative 1 plus the square root of 7 and minus the square root of 7. In the past, we've just been leaving our answers just like this because this is pretty. I just leave it. Life is good. It doesn't get too complicated. This, however, does not help me graph because even my teacher brain cannot really visualize where negative 1 plus the square root of 7 is on the graph. I really need this to be in decimal format if I'm going to graph it because that's just what makes sense. If you use your calculator and plug these in, you punch in negative 1 plus second square root 7 and enter, right? You guys know how to take square roots. If you do that, then you end up with a 1.6. And if you do the other version, you'll get a negative 3.6. Again, these orange answers that I just wrote down, That's the exact same thing as this purple stuff. I just put it in my calculator and changed it to a decimal, basically, so that now I can graph it. If the x-intercept is 1.6, that means it's not at 1 or 2, but it's right there in the middle. This graph is tiny enough that that's about as accurate as it gets, so don't get bogged down in how accurate 0.6 is. The other one is negative 3.6, so negative 3 and just a little bit more for the 0.6. Again, if I come back up to the top and pay attention to my original problem, I notice that it's positive. The x squared out front is positive. I'll leave it like that. So that means that when I sketch this thing, it's going to open up. Again, I don't know where my vertex is exactly. I just know that it's exactly in between the 2 points that I graphed right there. We don't know how far up or down, but we don't care yet. Last one right there. Same situation. I'm going to set this guy equal to 0 and ignore this guy right here. Just remember that the whole purpose of what I'm doing there, let me back up and show you this. It seems arbitrary that I'm just changing the y to 0. I promise I'm not just making that up. This actually comes from the definition of finding the zeros. Remember, the definition of zeros or of roots is it's where the dependent variable goes to 0. As we saw in our table, it's where the y's were 0. So that's why I changed the y to 0, is because that's the specific place in the graph or in the equation that I'm looking for. I need to know what happens to x when the y is 0 right there. Alrighty? Putting it over here just makes it look like what we've been doing for the last several days. So now it looks kind of normal, right? Solve it like normal. I'm going to run through this one a little bit faster since we've done this a million times. Oops, forgot to fill in the blank. That'll be a 9. 6 divided by 2 is 3. 3 squared is 9. Now I'm just square rooting both sides like normal. So you end up with x minus 3 equals the square root of negative 36. Okay, check it out. Here's where the craziness starts happening. You look back at example 4, you're doing everything this pot says, and you're trying to make that square root of a negative 36 work in your calculator, because your brain is telling you, hey, I can take the square root of a negative, or of a 36 anyway, right? That's going to give me 6. The problem is, when you try to do a negative 36, if you remember from Algebra 1, you're going to get an error. You cannot take the square root of a negative number. So what you have to know here is that, hey, this is where I'm going to get imaginary numbers. If I'm going to get rid of that radical, I'm going to have to do some pretending. Here's how you do it. Start by taking the square root of the number itself, whether you use the calculator or your brain. So my brain says, hey, the square root of a negative, or excuse me, the square root of 36 is 6. The square root of the negative, now that's the problem. So whenever you have to take the square root of a negative, you write an I instead, that little script I. That's how you write it. Square root of 36 is 6. The square root of the negative is I, because it's imaginary. Now I finish this up by moving my 3. So x equals, be aware right here that the imaginary term and the real term can't go together. So the children just walked in. You're getting voices in the background here. But anyway, you're going to write this as 6i. Oops, sorry. You're actually going to write it as 3 plus or minus the 6i. Because remember, when you take a square root, you get 2 versions of it. This time it just happens to be imaginary. Good news for you is you can't really graph imaginary roots because remember, they don't really exist. So in this case, you just kind of use your brain, or hey, you know what, use your calculator. Plug this puppy right here into y equals and graph it, and you'll notice that it looks about like this. At first glance, you're going to graph it and not see it. That's because it's up at the 45, way up here. You'd have to zoom out to actually see it. We know it opens up, though, because the quadratic opens up. Hey, and good news, if I didn't tell you already, our calculators came in. We should have them in the next couple of days after Mr. Johnson gets done engraving them and putting them all in the computer system. Awesome, right? Woohoo! So, backing it up real fast, look at example 3 again. Let's take this last moment now and identify the kind of roots that we're looking at. So look right here. See these right here? if you go back and you think about those, are those real roots or imaginary roots? And how many of them did you get? Well, I look and I see that there's 2 of them, and there's no i's involved, so I can say these are 2 real roots. I'm also going to say that they're rational. This is a new word. There's 2 of them because it crosses twice. They're real because I can really touch a -3 and a -5 on the graph. They're rational because I can write them as a fraction. Remember, -3 over 1 and -5 over 1? Hey, that's a fraction, right? And they're roots because that's what we've been studying. The second one right here, same situation. I'm going to look right there and go, okay, how many do I have? Well, there's 2 of them. They're real because I can touch the 1.6 and the -3.6. See, I did them right here in orange. They're 2 and they're real. This time, however, they're irrational, because I did the square root thing and I got a crazy decimal. Those are irrational. They don't make as much sense as plain real rational numbers. You know, if you're rational, you're making sense in life. Irrational, not so much. Oops, sorry, it jumped. So that was 2 real irrational ones. And lastly, be careful here. When you look at that, it looks like 1 answer, but remember, it's really 2 answers because of that guy right there. So here you're going to say there's 2, but they're not real this time because remember our I? 2 imaginary roots. And we don't have to worry about whether imaginary are rational or irrational because they're fake. They don't even make sense. That's it. If you're in Accelerated, please make sure that you write those questions in your summary. If you're in regular Algebra 2, then you just make sure you get back to class with your notes all fabulously copied. We will do questions and summary in class. Hope you guys are having a great day, and we will see you in class.